Kanishq, and it is said that fact is sometimes stranger than fiction. And now, here in the case, it's more true. In the case of black holes are something stranger than dreamt up by the science fiction writers, but they are firmly the matters of science fact. The first discussion on the black hole was held in 1783 by the Cambridge man John Michael. His argument ran as follows. If one fires a particle vertically upwards, such as a cannonball, it slows down due to the gravity and eventually the particle will stop moving upwards and will fall back. However, if the initial upward velocity were greater than some critical value called the escape velocity, gravity would never be strong enough to stop the particle and it would get away. The escape velocity is just over 11 kilometers per second for the earth and about 617 kilometers per second for the sun. Both of these are much higher than the real speed of the cannonballs, but they are very low compared to the speed of light, which is 300,000 kilometers per second. Thus, light can get away from the earth or sun without much difficulty. However, Michael argued that there would be stars that were much more massive than sun, which had escape velocity greater than the speed of light. We could not be able to see them because the light speed they sent would not drag back by the gravity. Thus, they would be exactly what Michael said and called them dark stars, what we now call them as black holes. To understand them, we need to start with the gravity. Gravity is described by the Einstein's general relativity, which is a theory of space and time as well as gravity. The behavior of space and time is governed by the set equation called by the Einstein's equation, which Einstein put forward in 1915. Although gravity is by far the weakest force known in the forces of nature, it has two crucial advantages over other forces. First, it acts over long range, and the second is a mystery for you. You can answer it below in the comment section. Despite these facts, the scientific community was slow to realize that massive stars could collapse in on themselves under their own gravity, and to figure that out how the objects behind them would behave. Albert Einstein even wrote a paper in 1939 claiming that stars could not collapse under gravity because matter could not be compressed beyond a certain point. If the amount of hidden information inside a black hole depends upon the size of the hole, one would expect from a general principle that black holes would have a temperature and would glow like a piece of hot metal, but that was impossible because, as everyone knew, nothing could get out of a black hole, or so it was thought. This problem remained until early in 1974 when Stephen Hawking was investigating what the behavior of matter be in the vicinity of black hole. Would it be according to quantum mechanics or just classical? To my great surprise, Stephen Hawking found that black holes seem to emit particles at the steady rate like everyone else at that time. I accepted that the dictum that a black hole could not emit anything. But he was Stephen Hawking. In 2016, together with Malcolm Perry and Andy Strominger, Stephen Hawking was working on using new results in their associated and conserved quantum properties. Find a possible resolution to the information paradox. We know that the three disensible properties of black holes are their masses, their charge, and their angular momentum. These are the classical charges that have been understood for a long time. However, black hole also carries a super translation charge. So perhaps black hole have a lot more to them than we first thought. They are not bald or with only three hairs, but actually have a very large amount of super translational hair. But what was remarkable of the discovery of the super translations Yes, it was that there are an infinite number of conserved quantum properties far from a black hole. It is these conservative properties, laws, conservational laws, and other that have given an extraordinary and unaccepted insight into the process of gravitational physics. The super translation here might encode some of the information about what is inside a black hole. It is likely that these super translational charges do not contain all of the information, but the rest might be counted by conserved quantities or calculus. Charges associated with some additional related symmetrics called the super rotations, which are as not still understood, but these ideas have just received confirmation with our most recent calculations. Quantum mechanics continues to hold, and information is stored on the horizon, the surface of the black hole. The black holes are still characterized only by their overall mass, electric charge, and spin outside the event horizon. But the event horizon itself contains information needed to tell us about what has fallen into the black hole in the way that goes beyond these three characteristics of the black hole has. People are still working on these issues, and therefore the information paradox remains unsolved. But I am optimistic that we are moving towards a solution. Watch this space.